This video is an extension to the previous video in which we discussed Favorskii rearrangement. Here we are going to talk about the Homo Favorskii and the Quasi Favorskii rearrangement. These are modifications of the Favorskii rearrangement, and in this video we will talk about the different starting materials that undergo these types of reactions and their mechanism. So let's begin. Right, so Homo Favorskii rearrangement is a type of reaction in which we have a beta haloketone. You can see here that we have this halogen at beta position with respect to the carbonyl or the ketone, and in this starting material we must have an enolizable ketone, or you can say that we must have an alpha hydrogen. So the reagents that are used is a base which can abstract this proton and an appropriate nucleophile, which we have discussed in the previous cases, like you can have water or alcohol or an amine as a nucleophile. So let's see how the mechanism works for this reaction. So this is our beta haloketone, and when it is reacted with a base, this base will abstract this acidic proton, forming an enolate, which when collapses back allows the removal of this halide anion, and as a result now we have an intermediate that is not cyclopropanone as we saw in the previous case, that is in the Favorskii rearrangement, but in fact we will have a cyclobutanone intermediate. So you can see here 1, 2, 3 and 4 carbons make up this cyclobutanone intermediate. The ketone is restored, and at the carbon next to this ketone we have this R1 group, and this carbon which is attached to R1 is now attached to this carbon here, which is further attached to R2, and then we have this CH2. In the next step, the nucleophile attacks the carbonyl carbon, forming this oxyanion. This oxyanion will collapse back to form a carbanion. Now, when this oxyanion collapses, there are two carbon-carbon bonds that can break. One is this one to form a carbanion at this position, and the other one is this carbon-carbon bond to form a carbanion at this position. Now, if both these carbons are symmetrical in nature, then either of these two bonds can break. But in this scenario, in the example that we have, the two carbons are not symmetrical. One is a secondary carbon, this one, with two hydrogens attached to it, and the other one is a tertiary carbon with three carbons attached to it and one hydrogen. So a breaking of this carbon-carbon bond will lead to the formation of a primary carbanion, and the breaking of this carbon-carbon bond will lead to the formation of a secondary carbanion. And we have discussed this scenario in the previous video as well, that if there is an unsymmetrical situation, then that carbanion will be favored, which is relatively more stabilized. So a primary carbonyl is relatively more stable as compared to a secondary carbonyl. So this collapse of the oxyanion will lead to the cleavage of this carbon-carbon bond, forming a primary carbonyl. So what we have as a result now is this carbonyl group with the nucleophile attached to it. Then we have this carbon here, this one, with R1 attached to it. And then we have the CH and R2 here. And then we have the CH2 with the carbonyl. And this carbonyl will then take up a proton from the solution to stabilize itself and form a stable product, which would look like this. So the CH2 is converted into a CH3. So this is Homo Favorskii rearrangement, which goes through a cyclobutanone intermediate rather than a cyclopropanone intermediate, as we saw in a normal Favorskii rearrangement. And again, if these two carbons are symmetrical, then any of the two carbon-carbon bonds can break. But if they are unsymmetrical, then that carbonyl will be favored, which is relatively more stable. And after protonation, it will lead to the final product. So you can have carboxylic acids or esters as the final product, depending upon what type of nucleophile you are using. Now let's see how the Quasi Favorskii rearrangement works. So if you look at the starting material of this reaction, the Quasi Favorskii rearrangement, there is no alpha hydrogen on this side of the carbon, and you see there are three R groups attached to it. So there is no alpha hydrogen available for abstraction by a base, but we have a halogen at alpha position. So again, it's an alpha haloketone, but there is no alpha hydrogen to be abstracted by a base. So there is no point in using a base here. So you can see here we only have a nucleophile. So let's see how the mechanism works. So here is a alpha haloketone without any alpha hydrogen, and we have the nucleophile. Now, because we do not have any alpha hydrogen, so no base is involved, only the nucleophile is there, and this nucleophile will attack the electrophilic carbonyl carbon, forming an oxyanion like this. This oxyanion will collapse back, and because we have this X group as a good leaving group, so this whole group on the left hand side, this will be detached from this carbon here. It will attack this carbon, allowing the removal of the halide anion and forming a stable molecule that will look like this. So the carbonyl is restored now with the nucleophile attached to it, and this carbonyl is then attached to this carbon, which has R4 and R5 attached to it, and this carbon is then in turn attached to this tertiary carbon, which has three R groups, the R1, R2 and R3 attached to them. So again, you can see we have the final product as the carboxylic acid or the ester or the amide, but the mechanism is completely different because there is no abstraction of the alpha hydrogen, for a reason that there is no alpha hydrogen available for abstraction. So these were the modifications of the Favorskii rearrangement, the Homo Favorskii and the Quasi Favorskii rearrangement reactions. Stay tuned for more named organic reactions in the upcoming videos. Thank you so much for now.